Yeah.
Yes, it was a great pleasure to welcome TR Govindajaran, TRG to all of us, right?
Yes.
He was
Thank
going
you.
to tell us about ultralight dark matter.
Okay. Thank you. Thank
Thanks for-
you, Kenjo. I should have given the talk in Dublin itself, but as you can see, I have listed several places where I have given, and every time I have made an addition of 1 or 2 pages in my
Okay.
right now. So the last one is yours. So you have the maximum number of pages, because this is an ongoing program with few people, and it will be interesting to see the end. Okay. Okay. The plan of my talk is actually started from Dublin. And that I will try to tell. Schrodinger's work and the dark matter question. And this is 1, 2, 3 are my crucial things. The last few sections are for entertainment. You may enjoy it. Okay. So I gave a talk, if you remember, in on January 2018, up in Dublin, Dias itself, must photon be massless? And that was, I was asking that question because at that time my interest was in asymptotic states in QED. So I was trying to look at infrared problem and asymptotic states, which I had some interest. I had a lot of discussions with Ball also. So one of the ways in which one can solve the problem is give a small mass to the photon itself. So if it is slightly massive, will it affect in any experimental or any known data, etc. And the surprise was Schrodinger talked about exactly the same question in 1955. In fact, I was just late by about 50 years. So this is a paper from Dias with the postdoc Bas at that time. And he was asking this question, since massive photon will have 3 degrees of freedom, 1 extra degree of freedom, while calculating in black body radiation, energy density as a function of frequencies, should we multiply by 2 or 3 to account for the transverse degrees of freedom or 3 degrees of freedom? So the 2 was accurate because that produces a correct Stefan's constant, sigma t power 4. And it is experiment. You can't play with that. That's a data. So the question is, should I multiply by 3 now? Is the question. So this is actually a picture from Dias itself. It's a very interesting, nice one. So I thought I will click it. So the 2 or 3 was a question which was bothering both Bose and Einstein. And should we multiply by 3 to account for the additional longitudinal degree of freedom? Answer he himself gave in that paper. He said, no, you don't have to multiply. You should not multiply as long as the vector potential is coupled to a conserved current. D mu J mu is 0. Okay. Sorry. D mu J mu is 0. And then I hope you are able to hear.
Yes, we can. Yes, no problem.
Okay, fine. Only a small change in the S matrix contributions if F gamma is small. Okay, given this, he went ahead and tried to estimate the mass of the photon from whatever data you can have. So since he established that as long as the current is conserved, you will not find any change in the known experiment as long as the mass is very, very tiny. So he established a bound on the mass of the photon in 1955 paper. It's a fantastic, very nice paper. And he uses simply straightforward equation, which is del square minus m gamma square vector potential is mu naught J, where J is the current. And that has a solution which is here. It's a curl of e power minus mr by r with magnetic moment here. And then he used whatever available as data from Earth geomagnetic field. So there is a magnetic field on the equator and there is magnetic field everywhere. So use the thing. If m gamma is not equal to 0, there is some extra magnetic field, and compare that with the magnetic field at the equator, which you expect. From this interesting calculation, he came to this formula, which is 2 by 3 m gamma r square divided by 1 plus m gamma r plus 1/3 m gamma r square. Now, knowing the data from the Earth, he immediately came to a conclusion about the minimum, the mass which cannot be greater than something. Sorry, less than something. So considering Earth as a magnet, we can estimate the photon mass from the above formula, and he has given the mass as less than 10 to the power minus 47 grams. This is his estimate. I will give this in electron volt because it is more convenient for many of us. And this analysis based on geomagnetic data was improved in 1970 by Goldhaber and Niato. And they came to the conclusion by only one order of magnitude, 10 power minus 48 grams. So that is because the geomagnetic data was quite good, even in 1920s and 30s, about the magnetic field all over the Earth in several places. Now, this estimate, which you have, now people try to use it for galactic thing, and there is now estimate which is 10 power minus 56 gram, which is actually a lot of questions are there. So based on this, the particle data book now gives 10 power minus 48 gram or 10 power minus 49 if I'm right, and not 10 power minus 56, but they give the data but with a question mark. This is the current status of whatever we know right now. Is it is of the order of 10 power minus 48 and less. Okay. In electron volt, that is 10 power minus 16 electron volt for the 10 power minus 48, and for 10 power minus 24 is for the other one which we have. So actually we have a cutoff because we are more or less trying to find out how the electromagnetic field is falling off. And whatever experiment we try to do, we are not going to do much beyond what is the size of the universe. And that actually gives some kind of an upper cutoff possible. We don't have to go up to that. Now, there are laboratory experiments. Wavelength independence of velocity of light is one of the direct consequences of mass being 0. If mass is not equal to 0, then there will be wavelength, velocity of light will be different for different wavelengths. So for the same, from the same stellar object, there are various electromagnetic waves are coming, X-rays are coming, optical light, radio waves, and microwave, all those things. And from there, you can estimate what is the mass which is allowed, but it is not great. It is less than 10 power minus 42 gram. So Schrodinger's estimate was much better than this. And this is the current status. Now, how do we give the mass? The problem will be if you give a mass term for a photon to the Maxwell action, it breaks local gauge invariance. And still global gauge invariance is there. And this is the kind of problem which we will have. So the gauge invariance is lost. And there are problems with when you couple it to QED, a massive QED, etc., on how to handle the renormalization, other issues, because the propagators will show that k nu by m square or d nu by m square, which is a problematic one but at high distance. So the gauge invariance is crucially required. So Stuckelberg did a fantastic thing, and he solved this problem of discontinuity in the degrees of freedom and the questions about renormalizable issues. So what he did was essentially try to add one more field, which is a scalar field, which is called Stuckelberg field. and impose gauge invariance with both of them. And very interestingly, if we take the quantum field theory book of Tom Banks, they actually talk about QED in a massive QED because he doesn't want to handle infrared problem because it is more complicated. People know how to do it, but in a textbook, he probably avoids at the initial stages in this way. The question is what happens if the M going to zero limit for the infrared divergence and the question of local gauge invariance. So the Stuckelberg's idea was essentially for the local gauge invariance by adding an extra field, which is what I have written here, mu minus 1 by m d mu phi whole square, and the QED part is already there. Now, this has a gauge invariance, which is a local gauge invariance, which is psi going to e power I lambda psi, and then mu going to mu minus d mu lambda, and phi plus m lambda. Now, this has some kind of parallel with what recently we see from several thing about string-inspired stringy descriptions, which many people have done. Schroer is one of them. So, having that, now we can introduce mass by Higgs mechanism also. So you can introduce a complex scalar field, couple it, and break the spontaneously. And the Stuckelberg theory is nothing but the limit of the Higgs mass going to infinity, keeping the phase alone finite, so that the mass of the photon is finite. That is the way in which one can arrive at. It's a limit of that. So essentially, freeze the limit fluctuations of the Higgs, but keep the phase to play an important role. There are other theories which we know, which is called topological massive theory, coming from two-form field and being couple this B mu nu field to electromagnetic field by this B wedge F term. Then that also produces a mass, which is well known, topologically massive gauge theory. This is what is the thing. I will not talk about the Chern-Simons theory and other connections because it is irrelevant for my current program. So now what is the issue? Stuckelberg field does not interact with matter in scale of length 1 over m, Compton scale of 1 over m. In units of h bar is 1 and c is 1. But has energy. That extra degree of freedom is also having energy and it can gravitate. So can it contribute to the dark matter question, which we are not usually bothered about? Was what I was thinking around 2019 after giving the talk at DIAS. I started asking the kind of question. Now, I have to answer. Hello?
Yes, I just wanted to catch up what you're thinking. What can I see the Lagrangian again that you want to use?
Okay, so
you want to use
this is a typical Lagrangian. I will use later. I have to use impose this in Weinberg-Salam model itself. But this is simply
you're not putting in a mass square term for the phi field.
No. Oh, no.
And there's no potential for it. So how are you getting a Higgs mechanism here?
This is not the Higgs mechanism. If I do this, in Higgs mechanism, I essentially couple it to a complex scalar field. The field which is here, that phi field is the phase of that complex scalar field.
Oh, you want this to be the phase of the complex scalar field.
That's what the limit, whatever Stuckelberg did is the limit of U1, the Higgs mechanism.
Okay, so you put a potential for this. Okay, all right, then. Okay.
Can I ask a question, sir? TRG?
Yeah, sure.
Can I gauge away phi?
Huh?
Why can't I get rid of phi by gauging?
Then you, well, in principle, you can see if you gauge away, it will actually go to the interaction between the fermions. It will have an extra term.
There should be full gauge invariance, I suppose.
Yeah,
So I
yeah.
just
No, the
replace
full
pi
gauge
by
invariance is there.
Yeah.
See, for example, if I gauge this going to mu going as a new mu prime, then this E mu, which is there, will pick up that extra one, yeah, d mu phi, which will be coupled to the current.
but that is a conserved current.
Yeah,
Coupling
it
to
is a conserved current. It will not affect, as such, it will not affect the thing as a classical field theory. But if you do
How
quantum
can-
field theory,
So
if you do quantum field theory, it will affect.
classically,
It helps,
I'm confused. If
I think
it helps to cancel the infrared divergence problems. That extra thing. That is the point, because this theory is see, for example, actually theory as such, even in this Lagrangian is fine. There is no problem. Now you can ask the question, what happens in the limit of m going to 0? At that time, there is extra interactions which come, and it's like having the coherent, the definition of the electron as a gauge invariant for the thing. You can, instead of putting a path ordered a mu dx mu, e power I a mu dx mu, I could have simply put that phi itself. Okay, that is the way it is.
Okay.
Am I correct in saying that what you're doing is essentially using scalar electrodynamics, which describes superconductivity? So it's essentially the same model of superconductivity we did with the permeate field.
It is close to that.
Yeah.
In fact, it's partly inspired by what Anderson did in his work on the precursor to Higgs mechanism.
Yes, then I understand what you're doing. Okay, thank you.
So now I will go to this issue of dark matter. So I'm sorry, I'm giving a one-page introduction to dark matter, because this is a kind of a lecture given to several places where they were not familiar with that. So this is basically one-page introduction to that. Our universe is consisting of matter, dark matter, and dark energy. These are the percentages which are involved. From the rotation curves of the galaxies and also gravitational lensing, we get some data about all the three of them, and acceleration of the universe. And like Kepler's second law, we expect the velocity of the outermost planets, in this case outermost stars, to go at a lesser speed, but if they don't, they follow the curve which is called the curve B, whereas A is what is expected. So this was one of the reasons why the proposal of dark matter came into the being, that there is a lot of matter in the universe and in the galaxy which is not interacting with the regular matter, and but involves in the gravitational forces. So that is the main idea. Now there are a lot of other things which happen, but I will just mention some of them. So the dark matter question is, galaxy clusters mass distributions can be measured in independent ways. Radial velocities within the clusters, X-rays from the cluster spectrum give all these things. And the existence of dark matter is overwhelmingly supported. Though dark matter and usual matter are matter, they do not evolve from after the Big Bang in the same way, and because of the nature of their interactions. And dark matter does not interact, and the radiation affects CMB by gravitational effects, and they have differential evolution. And dark matter is very crucial for the galaxy formation itself, and there are several candidates for the dark matter. At weak scale, several. Hello?
Yes.
Hello?
Yes.
Okay.
Yes.
Hello? Okay. Can I proceed?
Yes.
Yes, by all means, yes.
Okay. At weak scale, several candidates from SUSY, extra dimensions, Little Higgs, etc. have been proposed. In fact, I'm not making any criticism or other things of other models. I'm only focusing on one other thing which I'm going to say now. From standard models, sterile neutrinos, macroscopic objects like primordial black holes, massive compact objects, they were also being proposed. People have modified gravity also, which is known as a modified theory of Newtonian gravity, and entropic gravity, etc., are also proposed. Now, light bosons from QCD axions and axion-like particles, that is also something which is proposed. QCD axions is one thing, but these are all like axion-like particles. And the fuzzy dark matter, which I call now, they are all is the model which I am focusing on. It suggests that dark matter composed of ultralight particles having Compton/de Broglie wavelength on cosmological or galactic scales, or at least very large compared to the Compton wavelength is quite large. And the mass is comparable to the order of 10 to the power minus 20 electron. This is a proposal which has been there for the past 2 decades, and several changes have taken place, and the several new candidates have been proposed with this kind of a mass. Now we saw Stuckelberg field, or you can say the phase of the Higgs field, complex scalar field, decouples from physical processes and only exhibits gravitational interactions and has mass in this range. So my question was, why not use that itself? So this is the thing. But the problem is the mass of the candidate is too small. They will travel very close to the velocity of light, or within bracket light, and decouple from early universe. And that will not help, because they will go so fast that it will run away. They will be decoupled completely. But that is where Bose and Einstein helped again. Earlier, it is Bose and Einstein's work which helped. Now, Bose again comes into the picture. If you look into the paper written by Bose and sent to Einstein, the paper actually contains some statements which are interesting, the original version of Bose's paper. He essentially was introducing quanta of photon, light, and then so he was doing statistical mechanics of identical particles, which are photon particles, photon quanta. And then statistical mechanics of that he was introducing by introducing the statistics. And again, he had the problem of the the number 2 to come. So he said that the particle photon has a spin 1, but with 2 degrees of freedom. He said spin 1, but 2 degrees of freedom. And that's what he wrote in his paper sent to Einstein. And Einstein actually corrected it, and corrected it with the statement that instead of calling it as spin, the spin degree of freedom, he called it as a polarization degree of freedom. But there was some confusion between them, because polarization, which we introduced for the wave theory of light, and now you are introducing quanta of light, and then US natural object is spin degree of freedom, and there was some confusion about it. And later it was proven that actually photon has spin 1 by interesting works which were done in Ramanujan. Well, actually it was done in Indian Institute of Science. Okay. Now the basic idea is this particle, after the work of Bose, Einstein, and I think they went ahead. Einstein realized that he can actually apply this to ideal gas of particles with different masses, the quantum mechanical, or with quantum mechanical ideal gas, quantum statistical mechanics. And he introduced a new phase, which is called the Bose, well, now it is called the Bose-Einstein condensate. And such a possibility was introduced by him. So this is the interesting thing. And interestingly, this 2024 is the centenary year of Bose's paper. 1924 was the time he sent his paper to Einstein, and this happens to be 100th year, and S.N. Bose Center, if I'm right, people from S.N. Bose will confirm that such a thing is being celebrated. And I've been asked to give a talk also, incidentally. So this is basically the thing. So in the FDM picture, we may treat the constituent particles of Stuckelberg particles which do not interact. The only thing is the formation of Bose-Einstein condensate needs a conservation law for particle number. The system should have a temperature below the critical temperature. Now we have a shift invariance which is broken by the mass term, which is a small amount, and approximate symmetry is there. And the critical temperature for relativistic particles of this thing is what is given in this formula here. And you can see that m gamma to the power 1/3 comes here. Now, so the ideal Bose gas is a quantum state of matter similar to ideal gas of statistical mechanics, and Bose statistics is used. While at large temperature, they behave similar to whatever we know as ideal gas. But only thing is at low temperatures, they don't behave and there is a new phase. So this proposal was made by Einstein, and that there is a new condensate which can be formed because the Bose particles tend to go to the lowest possible state unless temperature is far above that critical temperature. So BEC was obtained experimentally in rubidium-87 gas with a mass which is consisting of 86 GeV, and the critical temperature turns out to be nanokelvins. Now, very low value because of the high mass of the gas which is being formed, making up the gas. Stuckelberg particles which we are considering now, they have typically masses less than 10⁻⁻20 electron volt. So you can try to estimate what is the critical temperature using some kind of data which we know from the dark matter density, etc. And that temperature turns out to be very, very high, close to the temperature of Big Bang itself. And we need to give the density and the change in the density by the Friedman expansion. And such a calculation we can do. And the formula which we have for the radiation era, matter era, dark energy era, all these things gives me that equation number 9, which is supposedly the final dark matter density. Now we know the dark matter density approximately now. Using that, we can try to estimate what should be the dark matter density at the initial period. Now this is the Big Bang, and the thing which is, I keep this picture mainly to explain to the students in many places. Okay, employing this, we can get the relation between the observed matter density rho and the critical temperature required for Bose condensation. And turns out to be, if the mass of photon is 10⁻⁻19 electron volt, for this I use the dark matter density approximately now is supposed to be 1 proton per cc in the universe or in the galaxy, Milky Way galaxy. And the mass of photon turns out to be 10⁻⁻18 electron volt. The critical temperature will turn out to be 10⁻17 degrees Kelvin. Now, if you take 10⁻⁻22, I will explain why I'm bothered about 10⁻⁻22. The critical temperature is 10⁻19 degrees Kelvin. So it is very close to the temperatures at the Big Bang time. And if a condensate of Stuckelberg particles are formed, then they will remain a condensate much lower temperatures which we have now. So that condensate exists as a wave in galaxy or some scale which is very, very large. Okay? The scale of the largeness is fixed by what is the Compton wavelength of whatever particle which we are considering. So now we have assumed the current dark matter density can be explained in terms of completely Stuckelberg particles. And using the Friedman FRW metric and thing, we can find out what is called half radii of the condensates and their masses. We can try to do that. So this is the formula which is using the condensate behaves like a non-relativistic particle. We can try to substitute in Friedman FRW metric and the V as the potential. And then there is a paper by Witten et al. For the half radius with similar mass of the order of 10⁻⁻22. They called it as axion-like particle for their thing, but I'm trying to use the photon itself or the Stuckelberg particle. Now, the important thing is, which is, why is it having such a strength in argument is the dark matter is, for example, in the Milky Way, you will find there are several dwarf galaxies which are there, and the halos of the dark matter halos are provided by these dwarf galaxies. So this the galaxy and dwarf galaxies play a role in estimating the mass which we wanted. All other proposals for dark matter, they have a problem. One problem: you do a simulation with any candidate which has a different mass which is higher, and then try to find out what should be the dark matter profile density at the center of the galaxy. You will find that it actually blows up at the origin. But whereas we know that there are galaxies, very interesting, I'll point out some of them, where it doesn't blow up, and this was known as the cusp problem in astrophysics. In fact, I myself am learning many of these things now. So this is basically the idea. So what was done by this Witten et al.'s paper is Hui, Ostriker, Tromine, Witten in this thing. They have given a formula for half radius and the density at the center of the, say, whatever galaxy, the central density of the halo. And this is the kind of a thing. We use this kind of a formula and try to parameterize what are the allowed values. And we find that 10 power minus 22 or 10 power minus 23 electron volt seems to be a good estimate, but there is no hard and fast conclusion we can derive from these proposals. Finally, it should be less than 10 power minus 20 is what is the best we can do. Now, the basic question is Big Bang and early galaxies. Now, the dwarf galaxies and density profile without cusp problem is what is achieved by the ultralight dark matter candidates of this kind of a thing. And I'm going to have a prediction which I will tell at the end of the next thing. Now, the size of the dwarf galaxy, the galaxy which is, I will explain what is the dwarf galaxy in a minute, but they are all small galaxies, is of the order of 200 light years to even something like 10,000 light years. That is the size of the dwarf galaxy. They are all small compared to Milky Way and other galaxies, which have million light years or billion light years as a scale. The number of stars in these dwarf galaxies are of the order of 1,000 or maybe 10,000 or at most a lakh. This kind of number of stars will be there in these dwarf galaxies. Now, there is an estimate which was done by Shaposhnikov, assuming similar ideas that the photon is massive, and he was trying to answer this kind of a thing, that the thermal equilibrium will be reached for the transverse photons in about 50,000 years, which is what we call as the radiation era. But the longitudinal photon will not even do the equilibrium. But that is not completely right, but idea is more or less correct, that it will have longer time scale compared to the earlier the transverse photons. So this is kind of idea which was used by Schrodinger in favor of 2 instead of 3, because the longitudinal photons do not interact with matter. So now the dwarf galaxies, there are about 40 dwarf satellite galaxies around Milky Way. They are much smaller than the mother galaxy, with stars ranging from about 1,000 to 1,000,000, of the order maybe a lakh. Simulations with dark matter project 100 to 200 galaxies should be there orbiting Milky Way. But we have found out so far only 40 of them so far that has been identified. They are known as, this problem is known as missing galaxies problem in the galaxy Milky Way itself. Whereas we expect about 100 to 200, 150 galaxies by the simulations, there are only 40 or 50 are actually experimentally seen or observationally seen. Now, the problem could be because they are so faint. Some of them could be so faint because the number of stars are very small, and the faintness may be related to the fact that the number of stars contributing to the galaxy is very small, and it may be difficult for current telescopes to see it. But our current estimate of the Compton wavelength, if the mass is of the order of 10 power minus 22 to 10 power minus 24, indicates one prediction which I have now, which is the smallest galaxy cannot be less than of the order of Compton wavelength of the such a particle, which is 100 light years. This is typically 100 to 200 light years. And so far, we have not observed any dwarf galaxy less than some 300 light years, 250 light years. And I expect it, we may not be able to observe anything because the dark matter should play a role in galaxy formation itself, whether it is dwarf or big. And this will be a very crucial factor to hold the galactic mass together. Now, this is a back of the envelope estimate because I'm only looking at the Compton wavelength, but we can estimate it better. And that is the kind of calculation I'm trying to do with some of the collaborators around now. Now, there is a thing which was done by Ryuto, Woodker et al. They essentially considered Maxwell-Proca electrodynamics. But only thing is they have put the Proca, which means they have added mass term. So essentially they have considered classical field theory with electromagnetic the thing and looked at the stress tensor from that theory. And that stress tensor compared to the electromagnetic field, because of the mass term, there is some extra term due to the mass, which you can say as due to exactly the contribution of the longitudinal component of the photon. Now, if such a pressure imitates gravitational pull, and it is associated with magnetic fields of correlation length of magnetic fields in the intergalactic space of the order of Compton wavelength. Well, we know that Compton wavelength scale is a time when longitudinal photons start behaving in an important way, and only the very large frequency, very large wavelength or very small frequencies contribute through the longitudinal photons. So this computation which was done by Ryuto et al. Also agrees classically that there is some extra pressure, negative pressure, similar to dark matter due to the Maxwell extra term which is there due to the mass. This is an interesting paper which was there in the literature. Now, where can I find, is there a place where massive photon can make a difference in particle physics? Now, there is a theorem due to Landau-Yang theorem where massive spin-one particle cannot decay to two massless photons. This is actually Ball's favorite problem. And in fact, I learned most of it probably from him and Manolab. This is simply group theory, representation theory of Poincare group and Bose statistics. We don't need anything beyond that. It's essentially massive spin-one Proca Poincare group representation and compared with massless representation with polarizations, which you have, and use Bose statistics, which is very crucial. Photon has only two polarizations, and the vector perpendicular to the momentum vector, that plane, okay, the momentum vector is in K, the perpendicular vector is the place where two polarizations are going to be there. And amplitude for two photons with Bose statistics from one massive spin-one particle, if we try to construct, we have only two vectors, epsilon1 and epsilon2, and the K, and it should have the symmetry of the Bose statistics. If you try to construct any amplitude, that will turn out to be 0. So now what we can do is we can try to find out, and actually this can be avoided if mass of photon is there, because there is one more degree of freedom which will come, and we can try to find out the mass of photon through the branching ratios of Z going to gamma gamma, which is Z is a spin-one particle. This decay is strictly prohibited if the photon is massless, but massive photon with the extra degree of freedom can evade this theorem. And they do in plasma physics, people have made some estimates close to this kind of a thing, but in an entirely different context. So the improved branching ratio can provide limits on the mass of the photon, which is one of the interesting things which I have done part of the calculation, and I will probably let you know. The important thing is, after the two photons which are there, one will be a transverse photon and another will be predominantly longitudinal photon, which experimentally is very difficult to observe. So what you will see is one transverse photon and missing energy through the longitudinal photon is the only thing that can be done, and that kind of estimate is kind of thing which we have to do. I have made another generalization to this theorem also, which is sort of interesting. It's an aside. We can generalize this theorem easily to SUSY. For example, a massive vector representation in n is equal to 1 SUSY cannot decay to massless SUSY representation. Now we are talking about supersymmetric representation. For example, Z cannot decay to 2 14-Os also. Now, some calculations have been done, but I have not yet sent for publication. I'm trying to write it up better and also try to generalize for n is equal to 1, n is equal to 2 kind of thing. So I will leave it as an aside for this. It is unrelated to this work. Now, there is some interesting information which came after my return from Dublin, and that is the page which I have added here. So there is some interesting experiment observations which have been done, which is called pulsar timing array. In fact, in my institute, there are a couple of people who are working on experimental aspects or calculational aspects of such arrays. So essentially, they are looking at the neutron stars, the pulsars in Milky Way itself. And there are several of them, and they are trying to look at the information which is coming from various things at a frequency level, which is the frequency level is of the order of nanohertz. So with some 98% percentage, there is some problem with the whatever written, and there is some gravitational field humming. It is something like a CMB for electromagnetic spectrum. So this has been actually discovered with reasonable amount of confidence, and it has an interesting connection to the fuzzy dark matter which I'm proposing, or which many people have been talking about. It is also related to my kind of work. So the gravitational waves of the galaxy mergers of the early universe in all the places are affected by dark matter between pulsars. In the universe, in the galaxy, there are dark matter between pulsars, and the gravitational waves are affected by this dark matter, which is kind of a scalar particle of very, very low mass in our galaxy. And it changes the galaxy, measurements which you do from various pulsars. Now, they provide a noise to the various frequencies which you are receiving from the pulsars. And the expectation is it will turn out to be, if you try to do the calculations, which I'm trying to do, and the thing is, well, people have done earlier one calculation, but I'm trying to apply to the specific context of photon, longitudinal photon, and nanohertz, and what is the amplitude is going to be very, very small. And if the mass, what happens is the mass is greater than 10 power minus 24 electron volt, it will match with many of the things which are there. So far, we have been talking about the mass should be less than something. Now we are talking about the possibility of photon mass be as seen, whatever is the photon mass we see, should be greater than something like 10 power minus 24. And if this is proven to be, then that will be a good candidate for this thing. And this work for the scalar field connection to PTA, pulsar timing array, was done proposed by Rubakov earlier in 1309, but now they have experimentally seen the hum and the numbers closely match. Essentially, this number 10 power minus 24 electron volt corresponds to a Compton wavelength. It corresponds to a Compton wavelength. And the Compton wavelength is essentially the average distance between various pulsars which are there in Milky Way galaxy. If you take the average distance between them, that should be the Compton wavelength, which is playing the role here. And that is a kind of estimate. So the dark matter and BEC desirable, we refine our hypothesis and study the theoretical model. There are 3 parameters to be taken, and the various calculations I'm trying to do based on this beyond whatever I have already done. And I'm going through the kind of a thing. Now, next 10 minutes, I will try to shift to the gear and probably provide some entertainment for my proposals and some kind of remarks which might shock. Okay, changing gear. Einstein's, is there any question so far you want to ask? Hello?
Yes, hello there. We're listening.
I can make a remark. The
Go
Z
ahead.
not to 2 gamma.
Okay.
Z not to 2 gamma. It is coming because of Poincare invariance. Okay.
Right.
So
and Bose statistics.
And Bose statistics. So
Right.
Manolo, Arshad, Babar, and
Yeah,
I
I saw the paper. I know the paper.
Okay,
I know the paper.
All right. Let me tell for the others entertainment. We re-estimated. We did the calculation where there is spontaneous breakdown of Lorentz invariance.
That is a possibility. I'm not ruling out. I'm not saying anything against.
No, I am not challenging you. I'm just telling. Okay? But I am telling also that I talked to people doing experiments in LHC, and they were not interested in looking at this process because it will be completely masked. They claim it will be completely masked by background, beam dump experiments and so on. They can't see it. So they don't want to waste their time trying to look for a very small process.
I agree. That is one of my problems because the estimate is going to be so small, the branching ratio, that it is going to be extremely difficult to look for such small numbers in the background which is there.
Yes.
In fact, people have done, for example, your friend Saurav Rindani has looked into the same, is it going to gamma? But as you say, it is true that you have to break in the conventional framework, break the Lorentz invariance. And what they do is they consider a background of magnetic field. In a background of magnetic field, you can violate this because there is one more direction which will come, which also will break the Lorentz invariance because that direction will break the Lorentz invariance.
Yes.
So, and they have done the calculation, try to understand. But again, you are completely right. It's going to be very, very difficult to even make some experimentalists to be interested in this.
So
let
me just make one more remark. I'm not remembering exactly, but in the paper I wrote with Sanjo, okay, we did the Poincare group analysis at that time. Tensor product of 2 both symmetrized irreducible representations of the Poincare group.
Right.
What are the irreducible components? Then we found a bunch of such selection rules. I'm not remembering, it is something like any massive particle of odd spin cannot decay into 2 identical massless particles which are both symmetrized. Okay? Something like that. So things like both symmetrized to neutrinos cannot come with their identical shape. They are Majorana neutrinos. Then a massive spin one cannot decay into them. So these are all Poincare. So, however, here there is a question which some of you may know the answer. I read by papers, by people like Bohr's, that the reason is, the basic reason is gauge invariance cannot be implemented on a Hilbert space. There is a cohomological obstruction to doing that. Okay, and so for example, it's already in Weinberg's book why you cannot write a photon field on a Hilbert space. He proves that gauge invariance is emerging because of our insistence on writing mu. Okay, so if you don't write it, you can do everything, but you can't write some vector fields. So there is some cohomology underlying this. I have not been able to trace the proof of this cohomology. It is apparently a cohomology associated to the Lorentz group and this Chevalier Heisenberg sequence and so forth. But I don't know the stuff enough to tell. Okay, so this is just side remarks. Okay.
Yeah, when you come, we will discuss it. I am very curious about some of these issues.
Okay.
I don't know. Honestly, I don't know.
No, maybe I see that David is there. Maybe he knows, or maybe Charlie knows. I don't know.
Okay.
There is some cohomology. Hochschild is related to this Hochschild cohomology, but I don't know enough about it.
Yeah. Do you have anything to say about the generalization to Susi?
Susi, we did not look. Okay, we were not motivated. That's a real reason.
Okay, anyhow, it's a generalization to the super Poincare group. You can say that.
I understand.
That's the point. Okay, so let me move on. So the reverse gear sort of interest, entertainment partly, I'll just try to tell. So Michelson-Morley experiment established the irrelevance of ether as a medium of propagation of light. Now, Einstein actually made this talk in 1922 after giving general theory of relativity. It is actually a talk which he gave called Sidelights on Relativity. And he said to deny ether is ultimately to assume that empty space has no physical qualities whatever. The fundamental facts of mechanics do not harmonize with this. This is quoting from his work, from his talk. Recapitulating, we may say that according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists a within quote ether. According to general theory of relativity, space without ether is unthinkable. For in such a space, there is not only would be no propagation of light, but also the possibility of existence of standards of space and time. But this ether may not be thought of as endowed with the characteristics of ponderable media, which we know as consisting of parts which may be tracked through time. The idea of motion may not be applied to such a object which he wanted. This is one of his quote. This is the reverse gear 1. The second reverse gear is in 1951, Dirac in Nature asked, is there an ether? He answered, we can now see that we may very well have subject to quantum mechanics and conforming to relativity, provided we are willing to consider vacuum as idealized state, not attainable in practice. From experimental point of view, there seems to be no objection to this. We may make profound alterations to the idea of vacuum. That is the idea. The vacuum, quantum vacuum is the ether is what he's trying to say. So that is the reverse gear 2. And then followed by John Bell says that ether was wrongly rejected on philosophical grounds, which is what is unobservable does not exist. And the final person which I'm going to mention, authorities which I'm mentioning, is Laughlin. And the word ether has extremely negative connotations in theoretical physics because of its association in opposition to relativity. Unfortunate because stripped of these connotations, it nicely captures the way most physicists talk about quantum vacuum. The modern concept of the vacuum confirmed every day by experiment is relativistic ether, but we do not call it this way because it is a taboo. So these are the authorities which I quoted, and one can think of this kind of object like the PEC condensate existing as a wave-like object throughout the galaxy in many with different densities in different places may serve the purpose of what they were trying to arrive at by the meaning of whatever vacuum you want to have. And Dirac, actually I use this picture because there is Dirac in this picture, Satyendranath Bose is there, and in between Purnima Bose is there. She is actually mother of our Suparna Sinha. Ball for you. This is a thing. Okay. So now the one more thing is a very interesting paper which I used to laugh at when I was a student. This was a paper written by actually Bal also used to laugh. The group which is called the KP Sinha, Shivaram and ECG Sudarshan. And the viscous drag effect of ether, people were worried about because the proposal was affect ether as a medium for light to propagate was dropped many of the problem. It will disappear if it is taken to be some kind of a superfluid. And a new model for ether as a superfluid fermion-antifermion pair may be described by macroscopic wave function pervading the entire universe, and lo and behold, they make this remark and may account for the missing matter. In fact, at that time when they were writing this paper, they were not aware of dark energy, but what was being talked about was dark matter, because that was sort of known at that time, and they were trying to account for this dark matter with such a proposal. This is Sudarshan's contribution. But anyhow, I want to have a look at whether some of these things will make sense. Now, I'm going to give one more interesting thing. We go back to our black body radiation, which was done by Schrodinger in the earlier days, 1955. And we know that cosmic microwave background is one of the beautiful black body spectrum. So we can check what will happen to the cosmic microwave background if photon has a very tiny mass, and look for the change in the CMB spectral things there, and try to put limits on the mass of the photon from the deviation from the black body spectrum for CMB. So the density can be easily worked out now, which is the formula which I have written down here, and to the modified dispersion relation P square is equal to E square minus P square. And such an analysis was done by Julian Peake in Fist of Letters in 2013. And using this density, he estimated, comparing with the CMB spectrum, which you want to have, and what is the mass of the photon from there. And that mass turns out to be less than 10⁻⁶ electron volt. As you can understand that this estimate is very poor compared to better estimates we have from geological and satellite magnetic fields of Earth itself. So this is a very interesting thing. Even the CMB does not give a good photon mass limit if you assume the CMB is by the black body radiation of the light itself, electromagnetic radiation itself. So now he makes a funny remark in that paper, Julian Peake, that if you assume that that photon has mass and it can decay to a couple of neutrinos with likely much less mass, then if you assume such a thing, that is very good thing, then he estimates the lifetime of the photon to be 3 years. That's what he estimated. Now, with the mass of 10⁻⁸ electron volt, since the photon travels with almost the universal speed, the time dilation will enhance this extensively, and this translates to the lifetime to be 10⁻18 years.
Sorry,
Which is
hello? What is the photon supposed to be decaying to?
What is that?
What is the photon supposed to be decaying to in this case?
Well, he assumed it is to be neutrinos with a mass which is much less, zero, almost zero. It is that's why it's a funny calculation, but anyhow, I'm just quoting it because of some interest. So he estimated that actually the lifetime is 10 to 18 years in our with time dilation, and it is fine. There is no problem with that itself, with the age of the universe. Okay, so this is the thing. But now the Stuckelberg field or whatever complex scalar field which I want to give mass to the thing can be incorporated in Weinberg-Salam model. Because if I want to do this kind of a thing in a realistic model applied to gravity within the FRW metric, I should use the Weinberg-Salam model. And that's what I have written. Well, various people have written. And this kind of estimate with a detailed calculation is being done right now with some of my friends. Okay, now there are various works people have talked about. So there is a very interesting review work on Stuckelberg field by Rugge and Altaba. And Wally et al. Proposes holography can be formulated in terms of information capacity of the Stuckelberg degrees of freedom. These degrees of freedom actually, as you know, that interaction between the longitudinal component and the electromagnetic current, J mu is, you can integrate it, and most of it comes at only at the boundary, which is essentially holographic kind of effect. And kind of thing is what Dwali et al. Are trying to do. Now, I will not elaborate more on what Dwali et al. Have done, but this is the interesting thing which I get to get a full feeling for what has happened. Now, I'm going to summarize. So, my interest in this came from infrared question after discussions with Alok Ladda and many others, and also Bal, because we were interested in IMSC and CMI on the issue of asymptotic symmetries, which in fact Bal went ahead and did a lot of work, particularly coming from gauge invariance. And I essentially tried to go in the other direction. What will happen if the photon actually has a mass, which will solve my infrared problem. And this is the kind of a thing one reaches that we have to understand what is happening at a length scale, which is in a practical sense, the length scale which is required is that of dwarf galaxies, something like 200 light years. And that seems to be a good estimate for the mass of the photon. And as to the thing, we should probably now compare it with the real photon without electrons present, maybe massless. That is not the issue. But you always have, after the Big Bang, the plasma of electrons and leptons, everything at the Big Bang time itself, within 1 second, within that. And we have to find out what's the mass of photon or electromagnetism in such a background, which is the plasma background, and what happens to the realistic Big Bang expansion because of the mass, which is the effective mass in the presence of electrons and other electrons which are present. And this is the kind of a thing in astrophysics which I wanted to understand, and I'm trying to do some more work. But some of them are old papers on infrared question and how the thing can solve, either in QED or in supersymmetry. I did some work with this guy, Nikhil Kalyanpuram. And also now I'm doing some work with Shiv Sethi and Aditi, who is a student from Madras IIT, on the issue of plasma, electromagnetism in plasma at the Big Bang time, and whether it can provide a nice argument for providing, attaching a mass and attaching a meaning to the longitudinal photon of electromagnetism with plasma of electrons and other particles which are there. So this is the ongoing work which is there, and this is where I will stop now. I'll thank you. This is the end of my talk.
Thank you very much, Deirdre, for a stimulating talk.
Provocative.
I'm sure there's some questions.
Well,
Mark.
I have questions. By the way, the talk was very interesting. You have done very much more than
Thank you. I have a lot of fight with you.
what I have heard. Okay, but there is still the following question:
Yes.
What happens to non-abelian gluons?
No, I don't have a mechanism of Stuckelberg mechanism for non-abelian theory. In fact, nobody has. So I don't know.
Okay.
In fact, this is the work which people, I think Delbargo tried to do a mu minus u inverse d mu u. Instead of d mu phi, he put u inverse d mu u as a Stuckelberg generalization. But the problem is it has unitarity and renormalizability problems. So I don't know any nice mechanism of talking about non-abelian Stuckelberg theory. The only way is the regular Higgs mechanism, which is being done by whatever we know now.
So one more part, like we have been looking at the axion. Okay, you did not talk about the axion, but that is also a model people have proposed for dark matter. Okay.
Yeah,
Now,
but okay, go ahead. I
please.
will make a comment because I didn't talk about it because there's a slight thing. The mass estimates which are coming, they are much less than the mass estimates for the ultralight particles.
Okay.
And they don't seem to help in some of the problems associated with dwarf galaxies.
Okay.
That is the criticism about that's why they themselves are looking for axion-like particles, but not axions themselves.
When I said axion, I meant axion-like particles.
Okay, axion-like particle is possible.
Okay. So
this mass. It's nothing to maybe something which is nothing to do with electromagnetism, but it's a new particle which is there of mass which is 10 power minus 24 electron volts, 22 electron volts. It's possible. It's possible.
Let me finish my remarks. The axion-like particle, which I can call axion again, which is what Wilson took, coupled to the theta vacua.
Okay.
So it is possible to see with how the standard Pachequin mechanism coupling changes the expectation value of the QCD Hamiltonian in the presence of the axion with the theta FF dual term, the Hamiltonian. Okay, so the quantum state is changed like that. It changes the Hamiltonian. Okay, and so it changes the spectrum of the Hamiltonian, and from the preliminary results we have again with this gang of four, that is Manolo, Ashad, and Babar and I, we find that, of course, it is known that the spectrum is changed, which is influenced by the gradient of the axion field. Okay, so the axion density is very high and the gradient is very high. It will change the mass a lot. Otherwise, no. Otherwise, it will be very little. Like theta is that is 10 to the power minus 10 degrees, I think. So very small. So it appears that shift the spectrum in the Hamiltonian from in the gluon sector from being the standard Fock vacuum to something with a mass gap. Okay, so it will give a mass to the gluon in the presence of the axion, maybe. Okay, so
it's possible. Yeah, it's possible.
That might be another mechanism. We don't know. Okay,
that's
anyway,
possible.
It's a mechanism. We can rule out theta vacua. I don't know. That's okay. Okay. If you rule out theta vacua, it is gone. It's okay. Then these are issues. Okay, so we can check also. Just a remark. Okay.
Okay. Fine. That's possible. I agree with you.
Other questions?
Well, your model looks so close to me to scalar electrodynamics, which is a superconductivity, and the phase transition would then be a superconductivity phase transition. So I'm expecting that something has zero resistance here, that the charge carriers for your complex scalar field, that the charge of that scalar field has zero resistance, that it's effectively superconductor.
That
how would that be observed? How would I go about observing that?
See, these are all cosmological questions which that is the kind of thing one can attack here. So there it is only the dark matter and other implications for such a thing.
But there must be some. I mean, these charges that exist in the model. So, and they seem to be resistance free.
Yeah, in fact, I don't know the experiment. See, this will be sort of related to what Sudarshan and all have done. They are looking for that scalar being coming from some fermion antifermion pair or something like that. So it might be some kind of a superconductivity at the background which is happening, which is with very little resistance that is playing the role. I don't know, because the gravity also should be put in this framework, which I don't know how to handle that. I'm only trying to look at from the astrophysics side and with my friend's help, whether something can be said as of now. And I don't have an answer for your specific question.
Okay. I will hand it over to anyone else for any questions or comments. If not, I will stop the recording and we can chat more casually.